So in this video we want to look at the proofs of the equations of motions, which can be found in our maths tables on page 50. So in physics we have to be able to prove three of these equations of motion, which are these three here. And if you're studying applied maths, we also have to prove these equations of motions, but we'll use a slightly different format for doing that. So the first of our proofs is to prove that v is equal to u plus at. So we remind ourselves that v is equal to final velocity. So we start this proof with the definition of what acceleration is. So we know that acceleration is the change in velocity with respect to time. So we know that acceleration is a, and our change in velocity is the final velocity, which is v, minus the initial velocity, which is u, over the time taken, which is t. So all we have to do to get rid of the t on the bottom is to multiply both sides across by t. So if I multiply the left-hand side by t, I get at. And if I multiply the right-hand side by t, I'm left with v minus u. And now all I have to do is add u to both sides, which gives me u plus at equals v. In other words, v is equal to u plus at, which is what I'm trying to prove. If I go back to page 50 of my maths tables, we can see that the next equation down is s equals ut plus a half at squared. So a bit like maths, these equations are in order. So because it's in order, I can use what I've already proved, and I've just proved that v is equal to u plus at. So to start our second equation of motion proof, s equals ut plus a half at squared, we're going to start with the definition of what average velocity is. So there's two ways in which we can describe average velocity. We can say average velocity is our displacement over time, and we'll call that equation 1. And we can also say that average velocity is the initial velocity plus the final velocity divided by 2. So if we call that equation 2, what we can then say is that both of these represent average velocity. So if we equate these two equations, we end up with s over t equals u plus v over 2. So if I try and isolate s on its own, I need to multiply both sides across by t, which gives me s on the left-hand side and u plus v over 2 times t on the right-hand side. So multiplying out the brackets on the right-hand side, that gives me ut plus vt all over 2. And as I said a minute ago, that we can use what we've already proved. So we know already that v is equal to u plus at. So if I replace the v in this equation with u plus at, making sure I'm using my brackets, all over 2, then if I simplify the right-hand side there, I get ut plus at squared all over 2. So if I add the like terms there on the top, I can see I have 2ut plus at squared all over 2. And if I divide everything on the top by 2, 2ut divided by 2 gives me ut, and at squared divided by t is the same as saying a half at squared. And of course, that's the second equation of motion that I wanted to prove. So just revisiting page 50 there, we can see the third equation of motion I need to prove is that v squared equals u squared plus 2as. So this is the third equation of motion, which now means that I can use the two previous equations of motions that I've just proved. So to start this proof, we're going to start with what we already know about velocity, in that v is equal to u plus at. Now clearly I can see that I need a v squared in this equation. So to get a v squared, I'm going to have to square the left-hand side. But if I square the left-hand side, I have to do the same to both sides. So what I do to one side, I must do to the other. And therefore, if I square out the right-hand side, I square the first term, so u by u is u squared. I multiply my terms and double it, so that's going to be 2uat. And I square the second term, which is at to be squared. So remember that it's at by at, which is a squared t squared. Now if I compare that to what I'm trying to get, I can see I have the v squared and I have the u squared, and what I need is a 2as. So I'm going to factor out what's common. So I can see what's common here is an a, and I need a 2, so I'm going to take out the 2. So watch what happens when I take out the 2. So I have v squared equals u squared, and I'm going to factor out 2a from the last two terms. So if I factor that out from these two terms here, I can see if I take out 2a from the first term there, I'm left with a ut. And if I take out a 2a from a squared t squared, well, there's no 2 there, so therefore I have to be left with a half. And if I take out an a, I'm left with a and t squared. So if I check, 2a by ut is 2uat, and 2a by a half at squared gives me a squared t squared. But if we notice, what's inside here is ut plus a half at squared. And if we remember, if we go back to our maths tables, that's the second equation there, s equals ut plus a half at squared. So if I say dot dot dot, s equals ut plus a half at squared. So of course that leaves us with exactly what I'm looking for. V squared equals u squared plus 2as. So therefore that's our 3 equations of motions proved.